See, the brief summary of CFT includes first, what are the basic assumptions? The assumption is the interaction between the metal and ligand is purely electrostatic, which means ionic. The central metal atom is observed as a positive charged species and the ligands as negatively charged species. In case if they are neutral, then the dipole present on that neutral molecule will be interacting the positive charge of central metal atom. These are the basic assumptions. Now you see, we always assume that it is the spherical charges which are approaching towards the central atom. Okay.
Yes.
Now, while metal has positive charge, at the same time, it also has surface or valence electrons in it. And it is these electrons, the valence electrons, which might start repelling with the incoming ligands. Okay.
Yes.
And due to this repulsion from the surface electrons, correct? The potential energy of the surface electrons will increase. All the surface electrons' potential energy will increase. Suppose if we are talking about the metal d orbital d block metals, definitely considering that the d orbitals are the valence electrons, then that outer surface is the one which might start gaining some energy first. So from here, let's say this is the increasing energy line. So in that case, from here, it starts gaining energy like this. And once the energy has gained, this d orbital might even split into multiple orbitals. Now, how the splitting happens depends on how many number of ligands that are approaching. For instance, if there are 6 ligands approaching the metal, the
Yes.
uniformity suggests that 6 ligands will be best arranged in the geometry of octahedral, which means if this is a central metal, we can expect the ligands in a way are approaching from all 6 directions of the Cartesian coordination. Okay.
Yes.
So one from x and minus x, y and minus y, z and minus z. Okay. Now you notice this. The d orbitals which are present as the surface electrons of the metal here, their orientations are different. Dx square minus y square will be along like this. This is the way it will be. This is dx square minus y square, isn't it?
Yes.
While dz square will be like this green one, if you can notice. This will be the dz square orbital. So we can say that these two orbitals, right? These two orbitals, which are along the internuclear axis or along the Cartesian coordinates, they will subject to have maximum repulsions from all the ligands, isn't it? Because they are
Yes.
oriented along that. So there is a head-on repulsion. While dxy, dyz, and dxz, they will be between the nucleus like this, between the axis. And because they are between the axis and there is not exactly head-on repulsions, they tend to have less repulsions. Okay. This set of 3 orbitals is what we call it as T2G. And this set of orbital is what we call it as EG. Okay.
Yes.
Now, this is a typical energy diagram that we can observe as the complex formation is observed. For instance, metal when it is in the ground state, it has some energy E1. As the ligand starts approaching it, the energy started to increase to E2. The amount of increase in the energy is what we call it as splitting energy, delta naught. Once it has increased, Now the splitting of the orbitals take place. Okay. The splitting should be such that the one set of orbital should have higher energy, the other set should have lower energy. Okay. Now you notice how much will be the rise of this. The amount of energy that it will be rising is by 3 by 5th of delta naught. For each set, for each electron, this much amount of rise will be observed.
Yes.
And how much amount of decrement will be observed here? Minus 2 by 5 delta naught. This energy line, which is the average energy line, is what we call it as barycenter. Okay.
Yes.
Now notice when the splitting happens, if this is delta naught, correct? From here, the splitting might take place into two ways. One, imagine I have 5 electrons in d5 orbital. Okay. One way of arranging them is give 3 electrons to T2G and 2 electrons to EG.
Yes.
Other way of arranging is, put all the electrons in T2G first. This is following uh, off-Bose rule. Got it? That is, fill the lower energy orbital completely, then only go to the higher energy orbital. Imagine this one. Whether it should go for this type of arrangement or this type of arrangement depends upon how much is the splitting energy. If the splitting energy is sufficiently high as compared to the energy required to pair, because if you are putting one electron with the other electron, they naturally have some repulsions. That repulsive forces are called pairing energy.
Yes.
And if delta naught is higher than pairing energy, then electrons will prefer to get paired instead of going to the higher orbit because it requires more energy there, isn't it?
Yes.
So usually, if delta naught is greater than pairing energy, molecules like this and all ammonia-based or carbon-based ligands, okay, phosphorus, ammonia, carbon based ligands, they are generally strong field ligands. And in that case, delta naught will be greater than pairing energy. I mean, in all those splitting. Hence, pairing is more favorable in this case. While if you notice here, if the splitting energy is lesser than the pairing energy, that means
Yes.
instead of pairing, it is much easier to go towards the higher state and get adjusted there, isn't it? So that's why the instead of pairing, excitation is more favorable. Okay. So all the halogens and oxygen connected groups, they are usually weak field ligands. Okay. So based on their field ligands here, we can say that this type of arrangement is observed when you have weak field ligands. This type of arrangement is observed when you have strong field ligands. See, the first 3 electrons will be same only, correct?
Yes.
So this issue of different uh, configuration will only arise between D4 and D7. Again, by the time D8, D9, D10 is concerned, again you'll have same configuration.
Yes.
So the problem only comes between D4 to D7, right?
Yes.
Notice. The total energy of the complex after ligands make a bond, right? That is what we call it as CFSE. How do we write it as a formula is like this. Number of electrons in T2G multiplied by minus 2 by 5 delta naught plus number of electrons in EG multiplied by 3 by 5 delta naught plus number of new pairs into pairing energy. Okay. This is the
Yes.
formula. You would better remember it like a formula only. Got it?
Yes.
Instead of fraction, you can write it in decimal form like this. Now notice one by one. If you have a strong field ligand, the first three cases are same, 1, 2, 3. Hmm? So in that case, T2G gets 1, T2G 2, T2G 3. For that, CFSE calculation is this value. Number of unpaired electrons are 1, 2, 3. This is the mu value. Fourth
Yes.
one, since it is a strong field ligand, you will be pairing it in the same position, isn't it?
Yes.
Now here is the interesting part. When it comes to fourth, when it comes to fourth one, you have introduced a pair onto it, correct? Because in T2G there are set of three orbitals. Now it will be 1, 2, 3, and fourth one. So a
Mm.
new pair has started, isn't it?
Yes.
Hence, you will write here as 1 into pairing energy. Most of the
Mm.
time pairing energy is ignored, but if it is very strictly written, you have to write it this as well. Okay.
Yes.
Next here, I'll be writing 2 into pairing energy because now you have making two pairs of it. Okay.
Yes.
Now here, I'll be writing 3 or 2 pairing energy beta. See, when you have T6, in the case of T6, imagine that when the ligands have approached, right? Before ligands have approached, there is already one pair existing, correct? In D6.
Yes.
In D6, D6, already there is one pair existing. Now,
Mm.
after splitting, it has become like this.
Yes.
Now, tell me how many new pairs you have created?
Two new pairs.
Two new pairs. So that's why it is 2 into
Mm.
pairing energy. Similarly, when you have D7, D7 means it is like this, correct?
Yes.
And you will be writing one electron here. Now tell me how many new pairs we have created? Only one, correct? Is that clear? In the case of D7. And if it is D8, D8, 0. So there is no pairing energy here. So what did you notice again? The pairing energy phenomena only applies to this configuration again, D4 to D7. Okay, right? And these are all the CFSE values. The highest CFSE value will come out as D6. So D6 is generally considered as very stable configuration. More negative value means more energy is released, which makes the complex more stable.
Yes.
Okay. Clear with these strong field ligands?
Yes.
Now, whenever you have cobalt plus 3 D6 configuration, because the configuration can give you a stable complex, right? If at all it is a strong field, correct?
Mm.
So the ligands like water, EDTA, oxalate, although they are very borderline ones, they are not very strong. But cobalt plus 3, when it approaches cobalt plus 3, they all behave like strong field only. So just like strong field ligand, you will make them completely paired into the T2G orbital and make it as uh, T2, T2G 6 electrons. Okay,
Yes.
right. Next, WFL, weak field ligands. In weak field ligands, there is no pairing. So you will see right from T1 to T5 here. So all of them you can see. First up to 3, it is the same thing. Fourth one, now you'll have 3-1, 3-2,
Mm.
4-2, and 5-2. Correct?
Yes.
And here is the difference between the strong field and weak field. That's it. This much. D4 to D7 is the difference what you'll find out. Okay.
Yes.
Here there is no pairing energy because you are not making any extra pairs at all. Okay. Right. The maximum amount of energy that you can release out here is half of what you get it in strong field ligand.
Yeah.
Okay. Right.
Yes.
Next. Generally, if it is been asked why chromium plus 3 is more stable than chromium plus 2 and manganese plus 2 is more stable than manganese plus 3, you can explain that on the basis of the complex formation in aqueous solution. For example, in aqueous solution, when it comes to chromium plus 3, it is stable because it has d3 electrons and it will make a T2G half fill structure. So chromium with 4 electrons will have lesser CFSE value compared to chromium with
Yes.
3 electrons, 3d electrons. Okay.
Mm.
Likewise, if you have manganese with plus 2, it will have d5 electrons, which means T2G will have 3, EG will have 2. Okay.
Yes.
So half fill in both T2G and EG will also bring some stability. And cobalt plus 3, generally T2G6 will bring more stability. Like I said, these all will act like strong field ligands in this case.
Yes.
Next is about 4 ligand system. In 4 ligand system, we have an option of geometry. Either it can adopt tetrahedral or it can adapt square planar. Okay.
Yes.
If ligands are approaching in a tetrahedral format, that means they are approaching from 4 directions to form a tetrahedral structure.
Mm.
In that case, the repulsion will be more experienced by this T2G set, which we have earlier seen, as compared to that of EG set. Okay.
Yes.
So therefore, initially energy will be less, and as the ligands approach, energy will increase. Thereafter, splitting will happen. Now you see that
Mm.
E will be here, T2 will be here. Now drop this G terminology here. In the 4 ligand system, we do not use that G terminology. That G basically represent Gerard orbital. Gerard means having, see, or when it comes to octahedral, the orbitals are all, these are all the orbitals which you will have, correct? After
Mm.
the structure formation. This would have symmetry, isn't it?
Yes.
This will have uniform symmetry. So whenever there is a symmetrical orbital forming, you call them as Gerard orbitals. Tetrahedral is unsymmetrical.
Mm.
So because it is an unsymmetrical form, we remove that G terminology. Okay. So we simply call E and T2.
Yes.
So in the E orbital here, you will see the amount of energy loss will be minus zero point 0.6 delta T, and here it will be plus 0.6, zero point 0.4 delta T. Delta T represents splitting energy of tetrahedral complexes.
Yes.
Okay. And since none of them, see, first of all, number of ligands approaching are less. So relatively, you are expecting, देखो, it is like this. For 6 ligands, you expect this to have some X amount of repulsion. For 4 ligands, how much repulsion will you expect? 4 by 6 times of X, correct? That means delta T will only fill two-third of what delta naught will fill, correct?
Yes.
Moreover, in delta naught, the ligands were approaching head-on. But here ligands are not approaching head-on. They are
Mm.
coming from sideways, like this, isn't it? Ligands are coming sideways. So again, another two-third amount of energy will be lost there also. Repulsion will be lost there also.
Yes.
So two-third into two-third. Two-third is because of the number of ligands. Two-third is because of the very bad orientation. So that
Yes.
into delta naught defines delta T. Okay. That's why delta T will be often equal to 4 by 9 times of delta naught.
Yes.
Usually, weak field ligands will only generate tetrahedral cases. Okay. Of course, strong field can also make tetrahedral cases. But in that case, the configuration is such where the d electrons will not be anywhere between 4 to 7. There has to be 8, 9, 10 cases, or D 1, 2, 3 cases. That's it.
Yes.
Now, in this case, if you have D1, correct, what will be the CFSE value? Let me again reiterate the formula here, that it is number of electrons in T2 into plus 0.4 plus number of electrons in E with minus zero point 0.6, that into delta T. Okay. So
Yes.
here if it is D1, so first it has to go into E. So which means it is minus zero point 0.6 delta T. Correct.
Mm.
Second, when it is D2, so it has to minus 1.2 delta T. Correct.
Yes.
Third, it has to go to T2, isn't it? So it will be minus zero point 0.6 plus zero point 0.4. So it is minus zero point 2 delta T. Okay.
Yes.
And next, if you have 2 and 2 here, correct? So 8 and that will be how much? 12. So minus zero point 0.4. Okay. Not minus
Yes.
zero point 0.4. Sorry. How much this will be? This will be zero point 0.4. Here I made a mistake. I have written it here. Sorry. Let me erase this. Yeah. Now you can see it better. Yeah. Now you can see that. So in case, if you have these cases, you can see minus zero point 0.8 delta naught. And then we have minus 1.2 delta naught. And if you have D4, it is minus 0.6 delta naught. Sorry. This one is for, that's why I deleted that. Sorry, I remember. Yeah, 1 second. Yeah, now let me rewrite this once again. Check out. D3, if you have, you should have 2 electrons in here, which means it is minus
Yes.
1.2. And here it is zero point 0.4. Correct? So
Yes.
minus 1.2 plus zero point 0.4 will make it how much? Minus zero point 0.8 delta T. If you have 2 and 2, how much that will be? Minus 1.2 and zero point 0.8. So which
Right.
makes it zero point 0.4. And when you have 5, it will become 0 again. And D6 means E3 this time. So it is minus 1.8. And T2 also have 3 electrons in it. Correct? So 3 means 12. So 18 minus 12. How much we have? 6. Zero point 0.6 delta T. And E4 this time. So 4 means 2.4. And here we have 3. So 1.8. So how much we have? Zero point 0.8 here. Next, E4
Yes.
and T24. This time T24 here. So 4 fours 16 and here 24. So 24 and 16. How much you will get? I mean 2.4, and this will be uh, plus 1.6, and the other one will be 2.4. So how much you will have? Minus zero point 0.8.
Yes.
Isn't it? Earlier, how much we got? Sorry, earlier calculation I made a mistake. Minus 2.4 and minus 1.2 here. Sorry. Uh, right. Next, you can see D9. D9, how much you will have? Because T2G is 5 this time, 20 and uh, 24. So zero point 0.4 delta T, and lastly 0. Okay.
Yes.
And number of unpaid electrons here is 1, 2, and 3, 4, 5, and here we'll have 4. Okay. 3, 2, 1, 0. Done. All good?
Yes. Yes.
This is one typical example. NiCl4 2 minus is one such example where we have four ligand system with weak field ligand. So it will go first electron will go start with E 1, 2, 3, 4, 5, 6, 7, 8. This is the configuration. So CFSE value will come out to be minus zero point 0.8 delta T. Okay. Is it all good?
Yes.
Now check out square planar complexes. When it comes to square planar complex, Navita, you started off with ground state. Now you have raised the energy to delta naught. That means you are in the background, you are assuming that there are six ligands will approach because they are all coming from axis, correct? Now suddenly imagine two ligands stop coming from z axis. So as usual, we expect that the energy should be splitted to delta naught for the orbitals, and thereafter it should be splitting into T2g and Eg, isn't it? But since here the ligands have not approached, two ligands have not approached, we can expect that the major stress that will be coming across is along the x and y direction now. This one. These two directions you will get the major stress now, major repulsion. Okay.
Yes.
That's why these two sets will undergo redistribution. And the electron the orbital which attains the maximum repulsion will be dx square minus y square. This one, the blue one.
Yeah.
Okay.
Yes.
And after that, it is dxy, which is also on the same plane like this.
Yes.
And then comes dz square. Dz square because this loop does not get any repulsion, but it has a circular ring around it. And that
Mm.
ring is on the xy plane. So that will get repulsion. So that's why dz square will have next best repulsions. The least repulsion are observed in dxz and dyz.
Yes.
So you will get basically four set of orbitals. This is set 1, 2, 3, 4.
Mm.
Each one will have a splitting energy of delta 1, delta 2, delta 3. The summation of all these splitting energies total is what we call it as square planar splitting.
Mm.
Okay. Now,
Yes.
although there are only four ligands approaching, correct? The delta SP value will be around 1.3 times of delta naught.
Mm.
Okay.
Yes.
So you can see the splitting energy is delta SP greater than delta naught greater than delta T. Okay. Now, nickel cyanide 2 minus, that would have a configuration like this 4s0, 3d8. Okay.
Yes.
And you see those 8 electrons, how they are distributed here. First, 1, 2, 3, 4. Then 5, 6, 7, 8. You have to keep on pairing as you start moving towards the next set. Okay. And now you have one orbital left that will be used for hybridization, and that's how you will get DSP2. Okay. In
Yes.
square planar, normally CFSE value is not asked because delta 1, delta 2, delta 3 is not given. Correct. But otherwise, configuration is being asked, hybridization is being asked in this case. Acha, any doubt here?
Yes.
No. Right, sorry, let me re-explain that. The factors that affect the splitting energy includes nature of the ligand, whether it is strong or weak. Iodine till water, they are all strong, weak field ligands. EDTA onwards till NO, these are all strong field ligands. Second is the principal quantum number of d orbital, which means if the central atom is 3d 4D or 5D. That also makes a lot of difference. Usually 5D will have very high Z effective. That's
Hmm.
why it can make any ligand into strong field.
Yes.
The same logic follows with the 4D also. So the concept of strong field and weak field is only observed in the case of 3D. So for 4D and 5D, everything is strong. Okay. Next. Next important aspect is the color formation. See, the color between the uh, within the complex, it could happen because of two reasons. One is DD transition, other one is charge transfer.
Yes.
DD transition is typically observed when the energy difference between T2G and AG falls in the visible region.
Hmm.
So when the white light approaches, the electrons present in T2G will absorb that light and go to the EG, and thus giving a complementary color. Okay. So one color of the white light will be observed. Rest will be white minus color 1. And that gives a complementary color, which we call it as the observed light. So this is the color wheel which suggests what is the observed light here. Okay. You got to remember the color wheel as well. So VI, BG, B, G, YG, YOR. And this is red purple. Simply you can write it as RP, red purple. Okay.
Yes.
Usually the absorbed wavelength increases from violet towards the red purple.
Hmm.
Okay. Now, imagine if the question was given like this. Okay. That there are four complexes. There are four complexes. One of them is blue, one of them is indigo, one of them is red, and one of them is yellow. Okay. These are observed colors. So this is what something which you are able to see. Okay.
Yes.
Correct. Now you have to decide which of them will be these colors. Which complex will take that color? Which complex will be blue? Which will be indigo? Which will be red? And which will be yellow? Given these four complexes. Okay.
Yes.
So how do we observe? How do we see that? See, it is like this. If BIRY, these are the colors what we are able to see, then what might be the respective complementary colors? Check out. For red, the complementary color is blue.
Hmm.
For yellow, the complementary color is indigo. For blue, the complementary color is red. And for indigo, the complementary color is yellow. Hmm? So in that case, BIRY, these are the absorbed colors. And which one will have the least amount of least amount of energy absorbed in this case? Okay. See, to avoid this confusion, let me rewrite that. Once again, I'll try to rewrite for you. Check it out. Imagine these are the colors which have been given to us. Hmm? These
Yes.
are the observed colors. Okay. And
Yes.
now I need to decide whether the observed colors and exactly matches with them or not. Okay. So this is option 1, 2, 3, 4. Which one is blue? Which one is indigo? Which one is red? And which one is yellow? That's what you need to decide. Hmm? So you watch the color wheel and try to put the complementary colors accordingly. Check out, we have B, I, R, Y, right? So what should be the absorbed, lambda absorbed? If it is blue color visible, it should be red. If it is indigo visible, it should be yellow.
Hmm.
If it is red visible, it should be blue. And if it is yellow, it should be indigo. Hmm?
Yes.
Now, out of these, if you compare, what should be the lambda? Lambda of red should be greater than yellow, greater than blue,
Hmm.
blue, which should be greater than indigo. Correct?
Yes.
Now, here the splitting should be the least between the orbitals. Here splitting should be slightly more. Here should be the highest. Here should be the highest. So
Yeah.
splitting energy will be the highest, in which case beta this last case. Okay.
Yes.
So if the splitting energy is highest, that means it should have the strongest ligand, strong field ligand. Out of
Yeah.
these four, which has the strong field ligand? Cyanide. Okay.
Yes.
So since here the lambda absorbed is the least, it will absorb indigo color and hence it is seen as yellow. So this is the yellow one. Okay.
Yeah.
Out of these three, the next strongest ligand is ammonia. So ammonia is the one which will appear to be red. Next one is yellow absorbed. That means it should appear like indigo.
Yes.
And the last one should absorb like blue. Does that make sense?
Yes.
That's how you should be able to relate the colors. Okay. Same way, if these are the absorbed colors, what are the observed colors? And which one is 1, 2, 3? Okay. Which one is red, which one is green, and which one is violet? You can see. Hmm? So check this question. See if you have understood that or not. This is a very generic theory. Whenever you are seeing any colors or if there are any electrons being transferred from inner to outer shells, they always have to follow this true rule. Two rules. First one is called Laporte selection rule. Second one is spin selection rule. So from an inner subshell, if it is going to any outer subshell, or from an outer subshell, if it is coming to the inner subshell by removing the electron, by pushing out the energy. In either case, the energy difference, the azimuthal quantum number difference between the orbitals must be plus or minus 1.
Hmm.
Imagine like this. There is an electron in 2p. If it is going to 1s, that means is it following the rule? Answer is yes. If it is going to 3s, is it following the rule? Yes. 5s, yes. If an electron from 2p is going to 3p, is it following the selection rule? No. Is it following here? No. Is it following here? No. If it is going to 4D, 5D, 6D, it is following? Yes, yes, yes. If it is
Yes.
going to 4F, 5F, 6F, no, no, no. Okay, correct.
Yes.
Now, have you noticed whenever we are putting an electron from T to G to EG, it is between D to D only, no? That's why it is
Yes.
called DD transition. Okay. That means when DD transition is happening, is it following the selection rule? No. Since it is not following, we call it as Laporte's forbidden. The transition is Laporte's forbidden.
Yes.
Okay. Second, spin selection rule, which means delta S is being 0. What does that mean? That means if an electron jumps from lower orbital to the higher orbital and its spin change is not observed, That means earlier if it has plus half as a spin, and after the excitation also if it is maintaining as plus half,
Mm.
then what is the difference in the spin? Zero.
Yes.
If the difference in the spin is zero, then we say it is following spin selection rule. Okay. Notice in the case of manganese plus 2, D5, this is the configuration of D5, and then when you are sending light, it will absorb one of the electron from T to G will absorb, it will try to migrate to EG.
Yes.
Now it is showing a DD transition. So that means it is Laporte's forbidden. That means it
Yes.
is not following selection rule. And if this electron has to go and sit here, it has to change the spin also.
Yeah.
If it changes the spin, then delta H will be greater than zero, which means it is not following the spin selection rule also. And usually, if both the rules are not followed, right? If both the rules are not followed, usually the complexes will appear very pale in color. And that's the reason manganese plus 2 will have colors which are very pale and typically pale pink. Okay. So why the intensity of color is less, that can be explained based on the type of forbidden nature they can show. Okay.
Yes.
So you can see this is a pale pink color. When it comes to charge transfer phenomena is a case where electrons from ligand are moving towards metal by absorbing the energy. Okay. Let's say this is the metal, sorry, this is the ligand which has some electrons in it. Okay. And manganese has an empty d orbital. In this case, for example, KMnO4 has empty d orbital. Hmm? So electron which is present in oxygen, which is preferably in p orbital, correct? What is the configuration of electron? 1s2, 2s2, and 2p4. So electrons are in p orbital, outermost electrons. That will absorb the energy and go to empty d orbital, correct?
Mm.
So when they go, the movement is from P to D. That means it is Laporte's following. It is following the selection rule. And electron, when it has to go from here to here, does it have to necessarily change the correct spin? Not needed, right? So the spin is also followed. Okay.
Yes.
This type of movement of electrons is called as charge transfer. And usually charge transfer always happens such a way that it is following both Laporte's rule as well as spin selection rule. When will
Yes.
you notice this charge transfer usually happens? When the central atom has very high positive charge or high oxidation state. Then only the movement of electrons from ligands towards metal is observed. Okay. This type of charge transfer is called LMCT, ligand to metal charge transfer.
Yes.
These are all those cases which will show LMCT.
Mm.
Colors may not be asked, but examples you should know,
Yes.
in what is the examples which fall under this category, LMCT. The charge transfer can also occur the other way around, that is metal to ligand charge transfer. The electrons present in metal are moving towards the ligand.
Yes.
In such case, ligand must have an empty pi star orbital or empty d orbital. Okay.
Yes.
These are such examples where you will see MLCT happening. Okay. Another type is MMCT. MMCT means
Mm.
metal to metal charge transfer. If inside and outside both of them are metals, then the charge transfer is called MMCT.
Yes.
Done, beta. Right. This is the
Yes.
part of CFT that you need to know.